can.
All right, thank you. Yes, so okay. So I want to give a lighter talk than the one that just preceded, and just explain ideas that are actually probably much simpler, maybe much more naive, much more in progress as well. But anyway, so lately I've gotten interested in the question of how much of this general program of homological mirror symmetry and what we've been developing over the years we can do when only one half of the structure is present. Usually we're lucky that both sides of our mirrors are Kahler manifolds or nice spaces, and we can do mirror symmetry in both directions. And so this is something, actually my interest in this kind of started when we had a discussion with Mohammed, Ludmil, and D.Auroux, where we thought of the Kodaira first-order manifold. And at some point we are going to write a paper about it, but I think the only surviving trace of that is a few comments about it in the introduction to Mohammed's ICM paper. So I guess this one is flat enough that by now Mohammed's technology basically handles it. Anyway, so don't try looking for this paper, it doesn't exist. But let's see. And just to tell you a little bit what was going on there. So the first-order manifold is a symplectic form manifold. Which is in fact a symplectic fibration by tori over two torus. That's the way it's usually defined, as a symplectic fibration by tori over the torus, whose monodromy is trivial in one direction, and the other one it's a Dehn twist. So you can also think of it as S1 times a quotient of R3, which ends up being basically the Heisenberg group with R mod Z coefficients. But so the observation is that this actually has two Lagrangian torus vibrations that are suitable for doing SYZ mirror symmetry. And one of them, which is the one I will be imitating more today, looks like, well, the base, affine manifold, has a fundamental domain which is, I guess, a rectangle or parallelogram or something, but when you glue together two opposite edges of this fundamental domain, you introduce a monodromy in the affine structure which is a shear. And so what you should imagine is if you take basically this base thing and then you take its cotangent mod the integer lattice, you actually build a symplectic manifold, and that's one incarnation of a first-order manifold. And so now the mirror to that would be basically the complexification of this picture, which means that now you think of instead something that comes from C star squared, but you quotient by a Z squared acting. In one direction not much happens, but in the other one you get the complexification of this. So it's something like Z1, Z2 goes to Z1, Z2, comma Z2, something like that. Okay, so mirror ends up being a Kodaira surface. And the other one has an SYZ fibration whose base looks standard, but has no Lagrangian section. And so this is what Mohammed was more interested in, I think, for his ICM paper, namely the observation that, in general, when you have an SYZ Lagrangian torus fibration, there's a cocycle that measures the obstruction to having a Lagrangian section, and that in turn gives rise, under family Floer theory, to a gerb on the mirror. And the mirror ends up being a jerk twisted abelian surface. So, all right. So that was very interesting, but then this is not the simplest example. The Kahler surface is not the simplest example of a non-Kahler complex surface, so it's the prototype of one that behaves like a Calabi-Yau. But nonetheless, you could ask, is there an even more baby example? And so the simplest of all examples, the Hopf surface. So that's the main example I want to talk about today.
Can I ask about this?
Yes.
So is there some sort of account purely in complex geometry of why those two things should have the same drive category?
Right. So from what I understand, there's not like a classical completely solid account, but essentially the story is that this is a Fourier-Mukai duality that you're supposed to be, this is kind of similar to Fourier-Mukai type auto-equivalences for usual abelian surfaces. You should imagine that if you have a Kahler surface, so it's a case unfamiliar. So a Kahler surface is an elliptic fibration over an elliptic curve, and but it's unusual in that it doesn't have a section. So all the fibers are isomorphic, but there's no section. And now you can look at the moduli space of, say, well, first we can take the relative Jacobian. You can take the pick zeros of the Jacobians of the fibers of this fibration. And that gives you another elliptic fibration. This one obviously has a section, because you can look at O on each of those. But the geometry of that is supposed to inherit a jerk that comes from this twisting. All right. So similar story for the Hopf surface. So now let me say that in more detail, and point out that this is project student Abigail. And there's further work in progress on other classes of examples, like products of higher dimensional spheres, but there's new challenges, so that's a different story, and I'm not going to get there, because I don't actually know for sure the answer. So, how does one get boards back to the top?
No, this one is kind of exception, so too quiet.
It's impossible. I lost it.
It's impossible. Yeah. No. You can get it.
Over there.
There's some hook on the right.
To the right.
To the right. Yeah. No. Close.
Turn to the
board. In the board.
Oh.
Yeah.
Okay. Thanks.
This kind of first desk is a little bit.
Okay. Thank you. I used to know this, but somehow okay. So again, so what's the Hopf surface? It's, as a complex manifold, it's what you get when you quotient c squared minus the origin by an action of z. So subgroup of a form q to the z. More explicitly, you identify the generator of z acts by diagonal multiplication. And for simplicity, here we will assume.
But it will not Calabi-Yau, yeah?
But no, it's not Calabi-Yau.
Unlike Kahler's surface.
That's right. So the Kahler surface is the Calabi-Yau case,
yeah.
And here this is non-Calabi-Yau, so the mirror will be something like a Landau-Ginzburg model of a symplectic kind, of course, since this is the complex set. So here, you can, for example, assume non-q less than 1, and here, in fact, I will assume that q is a real positive number, maybe q equals e to the minus a for some positive real number a, or there's a non-Archimedean version where you replace c by a non-Archimedean field, and the simplifying assumption I will make similarly is that q is just a pure power of t, of a variable. And the reason for that is I don't want to bother yet with things like B fields on the mirror or things like that.
Sorry, but so is the mirror going to be the naive guess, or?
I don't know the difference with the naive guess.
Okay.
Or it's just the Landau-Ginzburg model for P1 cross an elliptic curve and a jerk on top of that?
No, it's not quite that. It's very close to that. So you're right. The naive guess, anyway. Right. So I didn't say this is going to be a deep talk. You know, this is an easy talk. It's the afternoon. Okay. So no, there's not that much to it. Okay, but the site that could acquire a job would be this one. So you're right. So this is basically a twisted copy of P1 times elliptic curve. I will review that for people who are not into these things. And so it has a counterpart. In fact, this should have a Fourier-Bouquet counterpart, which is P1 times elliptic curve twisted by the job. And now the mirror will look a lot like the mirror of P1 times elliptic curve. So it will be a copy of C star times the mirror elliptic curve. But the boundary conditions on the Van-Ginsburg model will be slightly unusual. That's basically what will happen. Okay, so now I've given the punchline, and now I should explain a little bit what's going on. All right, so just in case you are not familiar with the Hopf surface, quick crash course. So this is, as a smooth manifold, this is the same thing as S1 times S3. So you have a fundamental domain between concentric spheres, so this is definitely not Kahler. As a complex manifold, this is fibered by the elliptic curve, which is C star mod Q to the Z. Fibering over P1, this projection is just the ratio Z1 over Z2. This fibration is locally trivial but doesn't have any section. Let's call that projection pi. Okay. And the thing that you might want to keep in mind is, well, what kinds of line bundles does this thing have? The Picard group looks like C star, and the reason is, well, you can build a line bundle, so it's called lambda, a non-zero complex number. I can build a line bundle by looking at Z1, Z2, V in, start from the trivial line bundle, but then you quotient by, so when you multiply Z1 and Z2 by Q, you multiply V by lambda. Quite a question.
In deformation theory of this guy, it's two parameters, presumably, yeah, because we can change to with different scales in Z1 Z2.
No, I have to keep the same scale for Z1 and Z2.
Why?
Sorry. You are absolutely right. So let me think for a moment.
Just changing the modules of the elliptic curve and changing the cost of the principal.
Yes. Okay.
So the second Betty number from here will go with the 2. This should be inverse.
But yes, okay. In a suitable sense, yes. All right. So, okay. So these things have sections if and only if lambda is actually power of Q, because in that case, lambda this is an integer, because then this is basically the pullback of O of n. P1 and the projection, and you have sections coming back from there. The fact is, in fact, L lambda restricted to a fiber of pi is basically the same kind of line bundle on the elliptic curve. So it's the point of the Jacobian of the elliptic curve that corresponds exactly to lambda. And so basically, if lambda is not a power of Q, then this is a non-trivial degree 0 line bundle on an elliptic curve, which is why there's no sections already even on a single fiber, or no. And no cohomology either. Okay, so so the practical thing that comes out of that is there's a lot of line bundles, but most of them don't talk to each other. Right, so if I look at X of L lambda mu, I will usually get 0 if lambda over mu is not a power of 2. And on the other hand, otherwise, it's basically lambda over mu, no, if mu over lambda is q to the n, an integer, and this is the cohomology of OP1 of n, times the cohomology of the structure sheaf of an elliptic curve. And normally there would be a spectral sequence starting at this, but it degenerates immediately. So what that tells you is you actually have an elliptic curve worth of completely orthogonal pieces, which each look like, well, a thickening of you tensor by cohomology of this S1, the derived category of P1. So this is what you have for line bundles, but of course line bundles do not generate all the things that we're interested in here. Because the restriction of any line bundle is something of degree 0 on each fiber, and you will never get, say, to skyscrapers of points, or to the structure sheaves, sorry, to the inclusion push forwards of any non-zero degree bundle on one of the elliptic fibers. Okay. So you might also ask objects of interest, and there's the line bundles that we just discussed. And there's basically sheaves supported on the fibers of this elliptic fibration. And I think you can check quickly that basically anything decomposes in terms of this. But this is not finitely generated, which means it has to be a little bit careful with it. Okay, so more towards non-symmetry. So the anti-canonical of this is in fact the pullback of O of 2, anti-canonical of P1, and which tells you that if you want to attempt some flavor of Strominger-Yauza slow mirror symmetry,
if you have the structure sheet and all the line bundles on the front.
Right, yes.
Does that generate?
I have the structure sheaf and all line bundles on the. So okay. So if I have the structure sheaf and all skyscrapers of points, then that works.
You're still finding the line bundles on the fibers.
Because fiber-wise, O and skyscraper of a point generate maybe of the elliptic curve. Oh, sorry. Oh, sorry. Okay, so if I take the line bundles and skyscrapers of points. Sorry, that's what I meant.
Okay.
The line bundles and skyscrapers of points generate.
And the structure sheet of the whole thing. Like,
Well, that's a line bundle.
No, but the structure sheaf is a line bundle.
oh, I see what you mean.
The structure sheaf is L sub 1. Okay, so I can take. Yes, so if I want something smaller to generate, I would take. My personal choice would be to keep all of these line bundles, and here just take skyscrapers of points.
So
that
the
would be
generator can
sufficient.
resolve the bag.
No, they don't resolve that. Can you pause?
It's not
I'm not sure.
Can you
Anyway, my homological algebra skills are not sufficient to prove homological mirror symmetry by actually studying all these things directly. And when you start seeing what should correspond to each thing, then you start saying that there should be literally there's probably a nicer way of doing it. Okay? Which is why this has an alternative title, which I will tell you about. Okay, so anyway, so based on the idea that this behaves like a Fano, sorry, not quite a Fano, but something with effective anti-canonical divisor, certainly, we want to remove that divisor before we attempt mirror symmetry. So we will look at the subset, let's call that X0, which is the inverse image of C star, for its complement of the fibers over 0 and infinity. And so this one is just C star squared mod Q to the Z. And so of course that one becomes completely boring and trivial, but maybe I should have said before, as soon as I remove one fiber from X, then of course I just have product elliptic curve times C.
Yeah, I got this question having to do with the title of this conference.
Yes?
So is there an approach to this kind of stuff where you take like a family of mirrors, this elliptic curve sitting over the mirror to P1?
So I do not know how to do that, but let's get to what I want to say, and then you'll see that maybe this is the closest I can do to something that's philosophically not that far from that. Okay, but I don't know how to do it. I don't know how to do it with mirrors to points, and maybe the problem is, if you want the points in the SYZ philosophy at least, the points that live on a circle of your base are represented by the same Lagrangian with different local systems. I do not know how to do a geometric gluing of objects that have the same geometric support but different local systems. So I need to include more as my building block. So, right. So the observation is, well, now I'm back in familiar territory because this is just a quotient, and this is really a C star times an elliptic curve, and this is like a baby SYZ. But I will continue to pretend that I don't know that this actually had a symplectic structure if I wanted one, because I don't need it, I shouldn't need it. So I will say anyway that x0 is filled by product tori. TR1, R2 is where fix say log norm Z1 equals R1, log norm Z2 equals R2. And so these are totally real tori, and in fact they are special. I don't know if there's such a thing as special totally real something for a holomorphic volume form with single poles on the divisor I removed, namely say d log Z1, d log Z2. And so what's going on here is now I can build, okay, so the other thing that is nice here is moreover these tori degenerate more or less in the usual expected way as you get towards the missing divisors, Z1 equals 0 or Z2 equals 0. If you attempt this kind of thing with products of higher dimensional spheres, then you hit new kinds of boundary behaviors, which is why this is a different project. Which is also interesting, but I'm not ready to talk about that one. So, but in this case, we have a usual kind of degeneration, but the T2s can collapse to S1 near Z1 equals 0 and near Z2 equals 0. And if you want, that's why we understand how the mirror will be a Landau-Ginzburg model. So, going back to the original philosophy of SYZ, or probably learn IHES slow and follow-up papers is the reference in this case, you would observe that you expect to build a mirror to X0 via what's called T-duality. Namely, you want to look at a moduli space of flat U1, say flat unitary connections on the trivial line bundle, that on this tori TR1, R2. Okay, and so this thing actually has a canonical symplectic structure. Which comes from the complex geometry. So maybe I should say what this space looks like.
It's not
yes.
for any family of totally real tori, you get it, it's complicated.
So
Uniformity,
I only know how to do it when they're special for some holomorphic form.
I see, yeah, special. I see.
Because in that case, right, so the way you build that is basically, you know, it's kind of the converse to the way that you get the analytic structure on moduli space of a Lagrangian torus vibration. So maybe I should mention it. Right, so the tangent space, you know, so if I have one of these totally real tori plus a connection, the tangent space consists of moving the torus around, and moving the torus around corresponds to vector fields which, when plugged into the holomorphic volume form, give me closed n-1 forms on the torus. So this corresponds to h upper n-1 in general. And of course, in this case, n equals 2, so it's usual h1 of the torus with the coefficients. And the connection comes from H1 on the other hand. And now there's a natural pairing where basically you wedge together the n-1 form coming from the deformation of the torus and the H1 element coming from changing the holonomy and skew symmetries. Okay. All right. So if you run this in practice on this example, you get exactly what you expect, of course. Which will be that we get a space with coordinates R1, R2, theta 1, theta 2, which you could say lives in R2 times T2, or it's cotangent of T2. This is a periodized cotangent of R2. This is C star squared, if you prefer. But mod, of course, we have to remember. So this was the mirror of C star squared. Then we have to remember that we quotient by rescaling by Q. And remember, I wrote somewhere Q is exponential of A. So this is mod an action of Z, where the action of Z just translates R1 and R2 simultaneously. So and so this is actually isomorphic to C star times the mirror elliptic curve, or if you want, T2, with area equal to Q, area equal to A, which is mirror to curve, but not in one single preferred way. There's actually two natural such identifications which will come up and explain basically what's going on. It's probably at least two identifications. Those two. Yes?
Is it correct that you begin with this usual mirror symmetry from C star squared to C star squared and then take a quotient by some...
Yes, that's exactly what's going on in this case, because in fact the Z acts just by translations on the SYZ base. So in fact they could have figured out what happened, starting from a symplectic side really by... So the only thing that's slightly unusual is when I do mirror symmetry for C star squared with C star squared, I'm allowed to think of both symplectic and complex geometry on both sides. But now the action that I have is only compatible with one of the two on each side.
Which is why this derivation needs checking at the end.
Yes. So, yes. Okay. Right, but so far we're not doing the interesting part, because so far, but Mohammed, what I'm saying so far, until I start putting boundary conditions,
yes,
is just the mirror to the open stratum, C star, the quotient of C star squared, which is just C star times elliptic curve. And I think we all agree that we actually know what mirror symmetry is for C star times elliptic curve.
yes. But why putting a divisor back into
Right. So the question is, yes, why does putting a divisor back into? So I will explain the heuristics first, and then we'll have to talk about what's going on. Yes. Okay. So the philosophy that we are supposed to follow of T-duality, moreover, is that if I have a holomorphic line bundle on my complex side, then it should give rise to a Lagrangian section of the vibration on the mirror. So I didn't say what my symplectic form was. There's a space. The one you expect. And you can check that this action is by symplectic morphism, so that's obvious. Okay. So now, all right. So if I have a holomorphic line bundle over X, I'm supposed to be able to equip it with a unitary holomorphic connection, with a metric and then a unitary holomorphic connection, such that the restriction of my connection to each product torus is fit.
Is it the line bundle?
Yes, line bundle. I'm only interested in line bundles because I'm trying to understand, just to give you some intuition for what's going to happen. Because we're interested in line bundles. I don't care so much about higher rank bundles here. Okay, so this is supposed to give me a Lagrangian section where So the r coordinates are basically the parameters here, and the thetas correspond to the holonomies on this tori. So I want e to the I theta 1 and e to the I theta 2 should be the holonomy of this connection on each torus as functions of R1, R2. So you can actually do this exercise explicitly for these line models L lambda and see what Lagrangians you get geometrically. So let's say that you use a parameter lambda, which is some power of q, that power is allowed to be a real number. So I'm actually restricting to a real direction inside my my Jacobian, and the reason for that is because if I want to see all of C star, I will need to equip these Lagrangians with local systems. But I'm not, sorry, these Lagrangians with local systems. I didn't tell you how to compute that. Okay, so to do the calculation using the most obvious metrics you can think of, you see something that looks straight out of mirror symmetry for P1. In some sense, it really is that. Oops, that's not right at all. Okay. And oh, minus signs, probably. Signs keep changing. Okay. So what happens is we have a coordinate in there which is R1 minus R2. And what theta 1 does is as this is not centered in the as R1 minus R2, observe, these are only functions of R1 minus R2, as they should, because after all, R1 and R2 separately are not coordinates. Anyway, so theta 1 runs from 0 to minus k, and meanwhile, theta 2 runs from minus k to 0. Okay? So if you look at only one at a time and not both, this looks a lot like mirror symmetry for P1, but in different ways depending on which angle you're looking at. Okay, so in general you might ask, well, is it a coincidence that some of these things go to specific values? And the answer is no, of course not, because if you're thinking of this intuition, what should happen now as your tori collapse onto S1s, as you get to the coordinate axis, is that the holonomy of the connection along the factor that gets squished to a point should go to identity. So that's the heuristics behind how to assign a mirror to this thing. And then, of course, one needs to check that it works. So the rule is basically here. As R1 minus R2 goes to minus infinity, so this corresponds to going towards Z1 equals 0. We need the holonomy along the S1 that collapses, so the S1 corresponds to the Z1 factor to be converging to 1, which means theta 1 goes to 0. That's the boundary condition I want to put when R1 minus R2 goes to minus infinity. And in the other direction, when R1 minus R2 goes to plus infinity, towards Z2 equals 0, I will impose that theta 2 goes to 0. So, okay, so this space, together with these boundary conditions, is what I want to call the symplectic mirror, candidate mirror to the Hopf surface. I will declare that I'm interested in a Fourier category built out of Lagrangian submanifolds of this symplectic manifold, which again is just basically a C star times T2. So if you think of, topologically this is R times S1 cubed, the R factor is this R1 minus R2. So at one end of the real axis, I will put a condition on the angle theta 1 has to go to 0. On the other end, I put theta 2 needs to go to 0, which is kind of slightly different from the usual. So let's briefly remind you that the usual mirror to the closest comparison point. The mirror P1 symmetric curve. That's also C star times the mirror curve, which is P2. But now the condition, so let's call this coordinate R and theta. And so the usual condition is as R goes to plus minus infinity, theta goes to 0. Okay, this is the usual story that the mirror of P1 is a cylinder with asymptotic conditions requiring that when you go to infinity or to 0, you do so along the real positive axis. Critical objects do things like that, and it's the same angle that goes to 0 on both sides, and here it's not. So philosophically, I suspect that this is, despite this boundary condition not being given by a global holomorphic function. See, here this came from the superpotential, coordinate x. This came from a superpotential of the form x plus 1 over x. Here there's not a global holomorphic function that implements these two boundary conditions. That's exactly the failure of this to be a complex Landau-Ginzburg model. But I suspect it also fits more or less in this formalism of, stopped Fourier categories or Liouville sectors, except this is not an exact manifold, so I shouldn't say Liouville, but maybe it's a non-exact sector thing.
So like locally near each component of the boundary, it looks like this.
That's right, and that's the key to how you actually hope to prove convolutional symmetry in that case, once you realize that. This example is actually an easy one once you see that. Okay, so why is it easy? Well, easy is maybe a big word, but...
How do you suppress the jerk?
There was never any jerk.
Well, why?
It never came up.
On the complex
I
sets,
think
we
the
always
germ
have
is
this
really
manifold.
twisting the potential. I think that's how the germ
That's how it appears.
is appearing by not making these conditions the same in two directions, then in one direction it's theta 1, the other direction is theta 2. It's my interpretation.
Because second convolution of rank 3 is going to get, yes.
Yes,
So
something,
three
yes,
parameters will be gerbil direction.
Yes. Oh, yes. Sure, yes, I never went into the exotic world. I stayed in very
Right,
basic.
but that's the incarnation of that twisting is.
Yes,
is
something.
the twisting.
Yes.
Am I supposed to expect that even though there's, maybe it's a stop category, and there's no holomorphic lambda Ginzburg model, but should I still expect a C infinity function to R squared or something like that, or to C? Is there some sense in which...
So for control of holomorphic this, it's going to be very easy because you're going to have maximum principle for R1 minus R2, basically. That's so in this case, it's going to be pretty...
Okay.
Or if you want... Yeah. Oh yes, so maybe also I should point out quickly, right, so what I expect to do with Lagrangian satisfying these conditions when I do vector homology, one possible way of saying it is I will perturb them by suitable Hamiltonians, and the suitable Hamiltonians, what they should do is they should modify this admissibility condition to instead have Lagrangians where theta 1 and theta 2 go to some non-zero constant epsilon, pushing in the correct direction, and I will see what I need.
Is it true that this space is glued from two copies of A1 times Z along
Yes,
with
you're stealing my punchline.
Oh,
But yes, that's exactly, yes, that's completely correct. Okay, so that's exactly how one will go towards the proof. But before explaining that, I want to point out, that if you look a bit more closely at these Lagrangians which correspond to the line bundles, well, first thing you see is, yes, they satisfy these conditions. The other thing you see, you could have seen before even that, is I want to point out that these are disjoint. This is disjoint from the zero section, or from each other. Unless, say, the difference of the values of k's is an integer. Remember, here k was a real number. And the reason for that is, after all, this satisfies theta 1 plus theta 2 equals minus k. So if they live at different values of, by projecting to theta 1 plus theta 2, you see right away that they cannot intersect unless the k's differ by integers. When the k's differ by integers, then basically you just reduce to mirror symmetry. If you look at the intersection pattern, it's really what you see is really the picture in the mirror of P1 times identical S1s in the fibers above. So you get K plus 1 intersections, as usual, after you perturb to include the ends. But above each of them, you get a clean intersection along an S1, which is how you get, I'll erase it somewhere, but at some point there was a statement that the X between these looked like things in P1 for all of K's tensor the cohomology of the structure sheaf of the electric curve. All right. You can also see, by the way, that when you look inside each electric fiber, I mean, what this theta 1 plus theta 2 equals minus K corresponds to in a suitable electric fiber is exactly the mirror to the flat line bundle to which these things restrict over each fiber of the elliptic fibration.
So what corresponds to points of your?
So very good question. So what corresponds to points? Well, so most points correspond to, you fix. So actually you fix basically fix R1 and R2 and let theta 1, theta 2 vary. That's the mirror to a skyscraper sheaf of point. But more generally, if you want to think of what lives, a sheaf supported on an elliptic curve, and that elliptic curve is not the fiber at 0 or infinity, then you have R1 minus R2, and here you will have basically. So here you need to put theta 1 or theta 2. We'll explain in a moment what I mean by or. And you take a circle here, and then the fibers of this map over here are elliptic curves, sorry, T2s, and you put the usual mirror to what you had on that elliptic curve, with suitable polynomials to adjust for value. Okay. So now, what should happen when you take fibers of pi that go to 0 or to infinity? That you've added new Lagrangians, which corresponds to one of them corresponds instead to something like this. So, that picture, right? This is that theta 2 goes to 0. So this kind of admissible Lagrangian arc that goes from infinity back to itself, going around the other end, is exactly the kind of thing that you add to the family of circles that you had when you start passing from compact Lagrangians to admissible ones. That corresponds to extends the family of skyscrapers of points by adding the point at infinity or at 0 for the other one. But so as Vivek pointed out, the faster way, so you could now start computing, and I completely trust that you could compute everything you want and it would always work. But because there's infinitely many generators, I don't actually want to have to compute everything. And there seems to be a nicer structural approach going on here, right? So the main reason that we have two different looking boundary conditions, of course, is because the way that the Hopf surface is built is by gluing together two copies of C times E over a non-trivial gluing map. And one can imitate that in the symplectic. So the observation is that the isomorphism between this space X, do they call that X? No, it's not X. It's a mirror. Let's call that Y. And so the point is that Y is symplectomorphic to a product, C star times mirror elliptic curves, in two different ways, at least. Okay. So one of them, remember the symplectic form was dr1 d theta 1 plus dr2 d theta 2. And I can rewrite that as dr1 minus r2 wedge d theta 1 plus dr2 wedge d theta 1 plus d theta 2. Okay, and now you see that r2 is mod A, so this is actually a symplectic form on a torus of area A with coordinates r2, theta 1 plus theta 2. And this one is a cylinder with coordinates r1 minus r2 and theta 1. Or I can do the opposite, d of r2 minus r1, wedge d theta 2, plus VR1 wedge d theta 1 plus d theta 2. And what's more, now if I use these modified coordinates implied by these expressions, you see that this first condition, theta 1 goes to 0 when R1 minus R2 goes to some extremity, looks completely standard in this presentation. Like this is the norm and argument of what I would want to think of as a complex variable, the C star variable, in this description. And the other one, similarly, corresponds to a norm argument condition on the C star variable in the second description. Okay? So, so in fact, the first condition, 1, is what I would call the usual notion of admissibility condition for the variable, complex variable, e to the R1 minus R2 plus I theta 1 in the first form, in the first chart, and 2 similarly corresponds to the same thing but for the other in the second chart. So what's going on is, in fact, we have a diagram of categories. And so the alternative title for this talk, but then I realized I don't understand anything of the subject, so I shouldn't play with fire, was that this was going to be, the alternative title was an exercise in gluing Fourier categories. Okay? So the interpretation here is I have a Fourier category with conditions 1 and 2 imposed. Okay? Objects are admissible Lagrangians with, well, both conditions 1 and 2. So theta 1 goes to 0 at one end, theta 2 goes to 0 at the other, and small perturbations. When we compute harms, we push the values of theta 1 and theta 2 slightly. This is the thing we're interested in. Now, these things have acceleration functors to partially wrapped Fourier categories, where I only look at one condition at a time, which means I do at the first end, R1 minus R2 goes to minus infinity, I still require theta 1 to go to a constant value, say 0, and I push 0 to a slightly different value for taking harms, but instead I wrap at the other end, R1 minus R2 goes to plus infinity. Okay? So this is implemented in various ways depending on your choices of techniques, but for example, you just turn on the wrapping Hamilton. And you have another acceleration functor, which instead forgets the first condition but keeps the second one, and you wrap at the first end.
And localizations here.
Yes, these are localizations. And of course, this, these two operations, you can just forget the whole thing and go to the wrap category of C star times equal. And this diagram clearly commutes. Okay? So this is mirror to. And then you might ask, how do I know that this thing is exact? So I think some very smart people like Shil, Vivek, and John Pardon have an answer to that. For their languages for exact things. Here there's a much faster thing you can do.
We don't have an answer to this.
Okay, you don't have, okay. Anyway, so in this case, there's a very easy way to do it, which is that you can do it by hand. Okay, because for line bundles, you can do explicit calculations. For line bundles, it just works because, well, we know what it is. In fact, you can just basically do it piece by piece for the various copies of things that look like the category of P1.
I thought you were going to tell me now that you were going to invoke your other students' thesis.
Well, maybe Zach knows how to do that. It's possible. Do you know how to do that?
You don't know Heather's thesis.
Yes. Well, this would have been Heather's thesis, except in this case, it's not quite Heather's thesis. But yes, essentially, okay. So you could invoke Heather's thesis. But in this case, that's overkill, because Heather is really good at introducing extra wrapping in the middle and wrapping counter wrapping, and this is not very helpful here. This is too small. Reverse thesis will come in overgluing exercises of this kind. Okay? But here it's not really going to tell you very much, I think.
No, it tells you exactly the
Tells you
special
this?
because cutting, I mean, rather than remove this side.
Oh yes, okay, yes, okay, sure, yes. So you could implement that as reverse thesis by implementing wrapping, counter wrapping on a smaller cylinder in the middle and thinking of acceleration as restriction, which is exactly what it is. Actually. Acceleration is restriction. But nonetheless, for the other solution, okay, so yes, Haverly's thesis, so either Haverly's thesis or explicitly, so explicitly what I mean by that is for line bundle it works because you can check, and all other objects are actually supported only on one side or the other side. So if you don't live near one end, then you go to the zero object in the appropriate pieces. So things that live, so compact objects live in all of those, but you get a diagram where you get 3 times the same thing with the exact diagram, it's the same as that. And so, yeah, so if you test against a compact object, it's clear. And if you test against an object that only goes to one end because it's supported on the fiber at 0 or at infinity, it's also clear because one side dies and then, right, 2 of them die and you're only left with this one, which is the same as what it should have been. Okay, anyway, it works explicitly. Okay, so for those who didn't follow what's going on, this is meant to be mirror to what you would get on the other side if you realize that the Hopf surface is a union of 2 open sets. U1 is the open set where Z2 is non-zero, U2 is where Z1 is non-zero. This is isomorphic to E times C by thinking of, well, just basically you can trivialize by taking a section of my fibration given by fixing Z2 equals 1. This is also isomorphic to E times C, but of course maybe here I should say instead this is C star union 0 and this C here is C star union infinity in terms of how they fit into the P1. Okay, and so I have restriction filters from DDFX to DDFU1, DDFU2 to DD of the overlap, which is E times C star. Now these pieces match exactly with those things because this one's the mirror to E times C star. And these ones, E times C, its mirror is basically the product of a mirror elliptic curve with the Lano-Ginzburg model C star with Z, which is what I meant by the usual admissibility condition at one end and prop at the other end. So that's probably a faster way of saying it, but it works. Okay, so now the question is what happened? You know, where's the non-trivial information? Where's the twisting here? So the way you can think of that is these 2 pieces on the overlap on E times C star, these things actually glue not in the usual way, where I would take identity on the elliptic curve and Z goes to 1 over Z, or in this notation identity, but rather by, so Z comma Y goes to Z and Z times Y. Okay? Sorry, I have my factors reversed. Wait.
So you can flat coordinates everywhere, yeah.
Yes.
I mean, you said at the beginning that this thing is E times C star in 2 different ways.
Anyway, so it's Z1 over Z2 comma Z1 and Z1 over Z2 comma Z2, and the way I get to there is that the factor that lives in the elliptic curve gets multiplied by the factor that's in C star. Okay. So perhaps so the diagram of category is really that, but if I think of how this fits in relation to, I have in my mind, when I see E times C and E times C star, I have already set in my mind how this should restrict, and these are the same, but now identified by a non-trivial autoequivalence, which is given by this gluing. Okay, the reason I'm saying it this way is because on the Fukaya side I get lost if I try to match them directly. It's much easier to say these 2 acceleration functors on the right half of the diagram are obviously the obvious ones if I work in these coordinates or in those coordinates. But the way the 2 halves match is exactly by this symplectomorphism. So we're saying basically the twisting here is by the symplectomorphism of C star times T2, which maps these coordinates to these coordinates. Okay? And so you can check that that symplectomorphism is exactly the cotangent extension of what you do to the base. So what you do in the base, on the R coordinates, is something like that. Well, there's a minus, my signs are all wrong and so forth. So it's a matrix of this kind that acts on the R's, and what you do on the thetas is the inverse transpose of that. That's the usual cotangent extension. So this is exactly what you expect to see in SYZ. And then the last thing to check is that indeed, as endofunctors of the categories for C star times elliptic curves, these match under mirror symmetry, which has not been done yet, but has not worked. Okay, thank you.
Questions?
I have two. The first one is, what if we switch A and B? Are we going to get the naive mirror there?
Sorry, so switch
If we
A and
start with a symplectic Hopf surface?
there's no symplectic.
There is no natural,
It's
but
just one thing
but
to
what
say.
if you take a degenerate symplectic structure?
I have no idea how to do mirror symmetry.
And the other question is, why isn't this working for Calabi-Ekman manifolds?
For what? For? Calabi-Ekman are these things like that are like products
Odd
of
dimensional
spheres,
spheres, yeah. I mean,
Yes,
you
okay.
can chop them up, you'll get
Yes,
cubical
yes.
diagrams
Oh,
like
okay,
that.
Yes, so we get diagrams like that. The problem is the gluing things on the functors involve things that are not compatible with SYZ in the usual sense. See, what happens here is you have a global S1 factor on your elliptic, on your Hopf surface. So things that are S1 times higher spheres, they
I
work
see.
the same way.
So if you take Hopf manifolds, it will work, but if you take
Exactly.
higher dimensional, odd dimensional spheres,
If
it's...
you take higher dimensional spheres, then, well, fear not, there is a diagram like that, but the interesting question is there a geometric meaning to this gluing of Fourier categories? And so that's what I have another student thinking about. What it boils down to in the simplest case of S3 times S3 is questions to, instead of now looking at the family of translations that push along the SYZ fibers, what about the family of translations, depending on the base, that translate the SYZ base of the elliptic curve. And as far as I know, what will happen is eventually it boils down to questions such as how do you understand actions on the Fourier category of the torus that switch around position and holonomy coordinates on the moduli spaces of objects. So you have two options for that. One is to realize them as idempotent summands in twisted complexes of correspondences. And the other option seems to be to revive this idea of coisotropic correspondences acting on Fourier categories. There's no way to do it directly with a single honest Lagrangian on the nose.
So you don't expect these complex manifolds don't live over the Webb covering anymore? I mean,
That's correct. I believe the S3 times S3 does not exist around. I mean, it's rigid, basically. The S3 times S3, you need basically, what do you need? I don't think it has any preferred large complex structural limit degeneration. Anyway, so all the SYZ fibrations were able to, and I think that's probably why all the SYZ fibrations were able to build, again, they're like Fano-like for SYZ mirror symmetry. So you can build the mirror to the open stratum, but what happens is that the degeneration behavior at the boundary is not the usual one. Instead of having fibers of qualitative things of lower dimension, you have things that collapse onto non-Lagrangian tori. You still have a geometry, sorry, non-totally real, sorry, complex thing. Things that are no longer totally real, but you can still make sense of the story. And it seems that there will be, we're hoping for a geometric interpretation where you have a mix of position conditions of this kind and holonomy conditions, such as when some real variable goes to infinity, the holonomy of a local system on our Lagrangian needs to satisfy some condition, which is basically when you twist it by some curved bundle, it tends to something flat at infinity. We think this is what is mirror to this kind of strange boundary conditions, but to be confirmed. Yes,
I
sorry.
have a question, yeah. It looks at story as some kind of extension of toric geometry, and in fact on this you observe the selection of C star square, yeah?
Yes.
And
yes.
one can also try to go through universal covers and universal. And yeah, it looks like complication not by usual orbits of tori, but some other orbits of tori.
Yes, I think so. Yes.
Yeah. So
So I don't know in general, how this would work in full generality. But again, so the case that's under control is very similar story for S1 times, say, a pre-quantum line bundle over a toric variety. Okay, so that works exactly in the same way. You just replace P1 by the toric variety everywhere. On the other hand, the more exciting ones where you don't see a global S1 factor, there's basically this issue that we don't know how to build families of totally real tori that degenerate to lower dimensional tori at the boundary.
yeah, but in general, just 35 orbits of C star square, we get quotients by C star square, maybe by some still discrete groups, and try to do like
Partial complexifications, that's right. So one could try to look into, I don't know what the classification of these things would be. It's a good question. I mean, certainly all the examples that we're looking at fit into this description. There may be yet other things.
Are there
Sorry,
any hope
Jay?
to use mere symmetry to classify type 7 surface?
That's a good question. But
yeah.
I wish.
Also, just a many years ago question. You consider
but what
SL2C
meaning,
divided
what
by
kind of
a discrete group.
support?
Yeah.
So kind of complex Calabi variety. Is it cannot be replicated for anything? Yeah.
That's it.
Yeah, it's very
Yes.
huge
That's
fundamental
also
groups.
good.
Yeah.
Yes. I don't know. That's a
Very
good
much.
question.
I mean, label all components of the information.
Okay, so maybe say.
Okay.